Hello, everyone. Thank you so much for joining us today. Welcome to our December webinar. This month, we are talking about geohazard risk mitigation. So as always, before I begin, I'm just going to run through some housekeeping notes. As you know, the webinar is listen-only mode. We also will have a Q&A at the end, so we're happy to take questions. Please feel free to put in your questions as the webinar goes along, and we will answer them at the end. The webinar is also recorded, and it's going to be sent out to everyone that's registered. And lastly, in the handout section, we've got our InfraGard and Rockfall brochure, so please feel free to download those. So now I'd like to introduce you to our speaker today, Peter Berger. Peter Berger is a seasoned professional with over 25 years of experience in geotechnical and geodetic measurement technology, data acquisition, and instrumentation. He combines his technical expertise with a strategic approach to industry leadership. His work continues to push the boundaries of innovation in geotechnical and structural monitoring. So over to you, Peter.
Yeah, thank you very much, Anna. Thank you. Anna is our Christmas elf today, so this is our Christmas edition of our webinar series here at Sensiv. Thank you for the introduction. What are we talking about today? Geohazard risk mitigation, innovations in wireless monitoring technology. So this is the content of our today's webinar. So we will have a quick look at summary about what we're doing at Sensiv. For those who are not familiar with our company, then we will have a short description what geohazards are, just to give you some context. And then we will talk about the growing threat and costs of geohazards, a very important topic. And then how we address geohazard risks with wireless remote condition monitoring. So we will focus on the wireless remote condition monitoring part. I'm aware, of course, that we have a lot of other technologies that are important in that field, like INSA, LiDAR, photo monitoring, geodetic monitoring, but we will focus on the wireless aspect. And then I have two short case studies to show you how effective risk mitigation can look like. And as Anna already mentioned, we will have a Q&A session in the end where I'm happy to answer your questions. About Sensiv, Sensiv has over the last 19 years been a name and a place of innovation. Since we have been founded in London 19 years ago as a spin-off of UCL, we have so far supplied more than 100,000 sensors into transport infrastructure and mining. We have expanded our team to a global capability. We have our head office in Milton Keynes, but you can also find us with distribution and support centers in France, in the US, and Australia, where we have a local team that can support you 24/5. And our monitoring solutions are for surface, subsurface, and structural applications. And we will also focus on InfraGard, our intelligent monitoring solution that is used in slope and rockfall monitoring. And we have also turned here Privian. Privian is our parent company from Canada, a leading technology company in non-destructive testing, which has acquired us a couple of years ago. Yeah, since our early days at UCL, our team has been growing to more than 100 people now from different disciplines, from civil engineering, surveying, instrumentation, and monitoring to advise and provide support to your monitoring requirements, but also telecommunication, mechatronic, electronic, to do innovation and to continue to develop our technology. So what is the key? The key is choosing the right communication technology in wireless monitoring. And we at Sensiv, we have two different options. One is the flat mesh intelligent monitoring, where we use the 2.4 gigahertz frequency to communicate between the nodes and the gateway to collect data. The specifics of this communication technology is that it's a very robust system that builds up a mesh network, allows using wider bandwidth to transmit data also in higher frequency, and we can also do network intelligence. And InfraGard is a term that we will see also later when I show you some examples. And what is really important is that when we select the flat mesh, it allows you fast reporting. It is the best solution for rockfall, for slope, and also for track monitoring and challenging monitoring applications when it comes to a reliable solution. And also the system comes with long battery life, and the gateway is fully solar powered, so deployment at remote locations is easy. But we as NCF, we also offer a LoRaWAN-based communication technology, which we call Geohazard. So basically, using the LoRaWAN frequency to connect nodes to a gateway in a startup network to cover larger areas like urban areas or mining sites where we have a large range, but it will come at the expense of lower reporting rates and less flexibility, and will not come with the network intelligence that we need for our rockfall and slope monitoring solution. So let's have a quick look what geohazards are. Of course, there's a definition for geohazards, which are natural or human-induced geological conditions or phenomena that pose risks to life infrastructure and the environment. Can be things like rockfalls, landslides, earthquakes, volcanic activities, or soil erosion. We see here in this image an example of a big rockfall event from western part of Austria that happened in July this year at the Siberetta Panoramic Road up high in the mountains, where a big rockfall occurred, and there we come also to the influence of climate change because the increased precipitation intensity leads to different effects, and also the acceleration of glacial melting destabilizes slopes and rock formations. And of course, there's also quite an important part of human contribution to this because of deforestation, urbanization, leading to land sealing, where we have the issues with water infiltration causing floods, but also mining activities and poor land management can contribute to geohazards. I have here an example from a rockfall event that happened in the Himalayan region. Why did I select this? Professor Paolo Mazzanti from Sapienza University recently posted this video from 2021 on his account, together with an article explaining the reasons for this event. It unfortunately led to people getting killed and the damage of infrastructure. But it also is important to understand the reasons. And in this article, if you visit his website or his LinkedIn page, you will find the explanation, and you will find also the key factors that I just mentioned in the geohazard definition. But we have a growing threat of and cost of geohazards. So if we just look at this year 2024, the first 11 months of this year, according to Swiss quick insurance, we had 300 billions in damages caused by geohazards. Yeah? And if you look at a smaller scale, maybe you can hear it from my accent from Austria, a small country like Austria, this year had 1.3 billion in damage, which is 30% more on the average of the last 10 years. So it's a growing problem and comes with growing costs. And when we look at examples, we have here a slide from our home market from the UK. Network Rail has a lot of earthwork assets, more than close to 200,000 earthwork assets that they have to manage over their 20,000-mile long network. And we see here soil cuttings, embankments, rock cuttings that expose a risk to the railway line. And, if we just look at the last couple of years, let's say the period between 2003 and 2020, there were 2,000 reported failures at the Network Rail network, which of course caused significant costs, delays, and problems for Network Rail. And they have produced also a very comprehensive report on earthworks. And this shows that the rainfall pattern, the rainfall intensity, which are important contributors to localized failures of rock cutting, soil cuttings, or embankments, has increased significantly. And when we look at certain events, like for example, a month in 2020, where in February we had in 1 month 250% more rain than on average over the last 100 years in February. If we look at 20 years back, we had 4 very, very wet winters that caused a lot of slope failure. So this is a problem, it's an increasing problem. And you see here also from this little animation, a slope failure and also an InfraGuard solution that we installed to monitor and detect the slope failures. network really spending a lot of money to maintain this repair earthworks, and just in the new budget CP7 season, they will spend 4.4 billion just on maintaining, repairing, and monitor their earthwork assets. But to look to a smaller scale, as I said, I'm from Austria. We also had a big flooding event in September this year, where the storm Boris, so we have the UK context again, caused heavy rainfalls in Central and Eastern Europe. And in this case, we had 2, 3, 4 times the rainfall within 2-3 days that we normally have in September. And this caused a big damage to the Westbahnstrecke, basically the rail line between Vienna and Salzburg. You can see in these images we had slope failures, we had embankment failures, we had tunnels and train stations flooded. So the damages estimated by Austrian Railway for just this section of their railway network was 100 million euro, and they managed to repair and get this up and running within a very short period. So by 15th of December, the Westbahnstrecke was up and running again. But this also shows that it's not only maintaining and keeping these assets in good conditions, but it also has something to do with of course, managing your asset and have monitoring in place to detect these problems and avoid problems like derailments. And just a final slide with some, of course, SENSIF context. This year was really a bad year, and just the last months, just to look at these images in Valencia, we had in October a big devastating flash flooding event, killing 95 people, damaging a lot of infrastructure. And our partner in Spain, Instop, went there to install sensors at bridges and damage infrastructure to monitor the infrastructure and keep it operational until they can repair it. Or in the center part, an image that was provided by our partner from Bosnia-Herzegovina. Also in October, a big heavy rain event damaging the Sarajevo-Ploče railway line, basically the main railway line that connects Bosnia-Herzegovina with the Mediterranean. Also, the railway line will be out of operation for many weeks. Yeah? Or damaged buildings from Poland, also a big flood event in southern Poland and Czech Republic, damaging thousands of buildings. And also our partner in Poland is providing now sensors. One of my colleagues was there to have a look how we can help, and these are things that are happening, and monitoring is important, not just before this event happens, also afterwards, in order to keep infrastructure up and running. But now, how can we address these geohazards? And for us, of course, we will look at the wireless remote condition monitoring aspect of that. As I have shown you in these slides, just to give you some context, how extreme weather events have been in 2024, not only rainfall, but also heat waves that have an impact on our infrastructure. And one consequence of this is that we have increased the activity of landslides, of rockfall events, interfering with our infrastructure. And having an early warning system, a monitoring system in place is important, especially when we look at these two images of shallow slope failures and rockfall events. It is crucial to invest in monitoring solutions. And key is our network intelligence. I mentioned that before when we looked at the different communication technologies we are offering. SENSIF can use the flat mesh network, the flat mesh technology, to use network intelligence. And one key aspect of network intelligence is sudden movement detection. Yeah? Because normally a wireless sensor is taking readings, for example, every hour. Yeah? But normally you would not know what is happening in between. Similar with a robotic total station, you measure and then 2 hours later you measure again and you get readings, but you don't know what is happening in between. And therefore, SENSIF has developed InfraGuard, where we have the sudden movement detection, where the tilt sensor, which is stored on a stake or the pole of a rock protection fence or in another structure, if there is a rotational movement or a sudden movement that happens, it causes a rotational acceleration, and the sensor will also wake up between the scheduled readings. So let's say you have hourly readings, you still, if an event is happening, and these events happen suddenly, you would still get the feedback from the event, from the sensor, because the sensor is basically always listening. And with this functionality, it's also important to understand if this is a real alarm, how we can send an alarm out quickly, and we will see then later the different components of InfraGard. But the flat mesh technology allows us, if a node has the sudden movement, detects it, wakes up, increases the reporting rate, sends out an alarm quickly, and does other smart things. This is what you will not achieve with another wireless communication technology. LoRa will not allow you to do that. You need the flat mesh technology. And when it comes to then understand what is going on site, it is not only waking up and taking a reading then every hour. You can also increase automatically the reporting rate, what we call dynamic reporting. Oh, sorry. So basically, from a baseline, you define certain thresholds, and depending on the rotational movement of the sensor, you can then increase the reporting rate. Basically, you have a baseline reading, the sensor rotates, and the more the risk increases, the more data you will get, and the more often the sensor is taking a reading. This is done dynamically, and also is then not only limited to one sensor, but it will expand to the sensor in the mesh network. So if we look at another functionality, which is key for the InfraGard solution, and everyone who is in instrumentation monitoring knows that we don't want false alarms. We don't want outliers, especially when we have a lot of sensors that are installed and we have a lot of data to look at. So this also helps you to understand if this is just a singular event or if this alarm is real. So basically, when you have one sensor that goes into alarm state, it will wake up the neighboring sensors to understand, is it something like wildlife interacting with one of the poles? That this is not a real alarm, it's not a slope failure. But if you then look at the other sensors and they also start to show similar movement, then of course you should be alerted, and you will then of course have the chance to verify what is really going on inside. And also to show you at least some hardware, some sensors of Sensiv on the slides. These are the two key components of the InfraGard solutions. So basically a low light camera that provides high resolution images on request or triggered by movement, and tilt sensors that allow you to provide your readings in the specified frequency, but also the accelerometer that is in there will allow you that the sensor wakes up between the scheduled readings and will then, what I showed in the previous slides, then come with all this functionality that help you then to detect the movement immediately. But still with long battery life, with low maintenance, all solar powered, so easy to deploy also at remote locations. So we mentioned sudden movement detection, and we have here a slide for slope monitoring, and this is a typical installation that we are doing at Sensiv. This is from our test site in Dudley, where we test our developments and our innovation. But these systems like that have been deployed at over 45 kilometers of earthworks in the UK, using InfraGard functionality to monitor the slopes, the earthwork assets. If a failure happens, provided with a camera allows them, the asset owner, to detect the slope failure, stop the train, avoid derailment, and of course then be able to manage the railway asset properly. But not only in the UK, this is also used at tailing dams for mining sites in South Africa and at earthwork in Europe, in the US. So quite a proven system to monitor slope failures. And here we also have a nice little movie that I want to share with you, and just to show you the different steps that I tried to outline before in a movie. We see here the stage one. Sensors are on standard reporting rate at the preset frequency. No movement is detected. We take readings every hour. The sensors are installed there, communicate every hour new data to our web platform. Every 6 hours, an image is triggered, just routinely. And then if something happens, a single node starts to detect a movement, is then increasing the reporting rate, is sending out an alarm, requests an image from the camera, so you can do immediate verification if it is some false alarm, like an animal hit the sensor, or if it is a real problem. And when this continues, the other sensors wake up, will then send again an alarm out, and of course will again provide an image, and this allows then the control center to potentially stop a train and identify a slope failure immediately without latency. And the other part of InfraGuard or Rockfall InfraGuard is that we have launched recently, also deals with impact. So it's not only rotational movement, there's also impact that we want to monitor and use the system then to provide the functionalities to wake up, to the dynamic sampling, to send out alarms. And when we look at the rockfall monitoring components, it is a modular system. We added to the tilt sensors, draw wire sensors, potentiometric draw wire sensors to also be able to detect, let's say, the impact of smaller rocks or medium-sized rocks. We added tilt meters for rotational movement and impact detection, and it can be combined with a camera in order to allow remote visual inspection of what is going on. And if a rockfall event is happening, of course, all this functionality happens. You send out alarm, you increase the reporting rate, sensors are waking up, and of course an image is triggered if you have a camera installed, and this allows you then immediate visual inspection of what is going on site. As I said, why these different components of the rockfall monitoring solution? If there are smaller rocks that are falling down, only the draw wires will show you that there is some extension of the draw wire, and potentially get an alarm. This will help you to understand when do you need to send someone else from the maintenance crew to clean or remove the material to allow the full capacity of the rock protection net. Medium rocks, also potentially only the draw wire will catch this. But if then medium to larger rocks hit the catch fence, there will be rotational movement, there will be impact detection, and and of course you will then know what is going on. Also, we have a nice little video that shows this functionality with the different components. You see here the camera with an edge up and also fully solar powered. You see here the draw wire sensors with a potentiometric crack sensor node installed at the catch fence with the tilt sensors on top. Small rocks falling down, filling up the rock protection net. Draw wires send out an alarm. Medium-sized rocks hit to larger rocks hit the catch fence, and potentially you have a catch fence with a design impact load of 1500 kilojoule. If this is above, they will start to rotate, you will pick that up. And larger rocks, if there's an impact, you will also get all the functionality from InfraGuard that is shown here. An image is triggered, and you can then decide what you need to do. Yeah? So we are good in time. So I have now a couple of slides with case studies from projects that where we have installed monitoring solutions or provided monitoring solutions to monitor rockfall and rock protection structures. One from Austria. I have two examples from Austria because I have been on site there, so I know what was going on there, and I can share some images. This is an example from the center of Austria, Bad See. There's a railway line, and there's also some problem with rock and with a crack in the rock above the railway line. And ÖBB, the Austrian Railway, decided to install crack sensors here to monitor that, and together with a gateway with solar power supply, you get a full year control of this crack. And you see here one of the crack sensors installed with an additional bracket. You see the seasonal changes as crack opening, closing depending on temperature. And this is more or less a 24/7 whole year solution. And with the sensors, with the crack sensor nodes that were installed there, ÖBB has a reliable solution for 10 years plus to collect data, and if something is happening, they can react quickly. Another example from Austria, also with Austrian Railways. This is close to Salzburg, or south of Salzburg. We have here again a situation where we have a rock protection net with, in this case, with 1500 kilojoule impact design load. Rockfall protection nets can go up to 10,000 kilojoule. Of course, then the installation is quite complicated. But here we have this situation. ÖPB decided that they want to monitor this area because we have, you see here up this rock formation where we have regular rockfall, we have a road below, we have a railway line, and on each pole a tilt sensor was installed and the camera to allow visual inspection. And in this case, we can also show you how the system has worked. This year in June, you know, the image was taking, or the camera was taking an image at 6 o'clock in the morning, 4 times a day, 6 o'clock standard photo. But then at 9:17, you see here some smaller rocks started to fall down, hit the net, of course, triggered then, you know, the impact detection, triggered an image. ÖPB was aware, oh, something is starting there, we need to be careful. And an hour later, the real event happened. Larger rocks were falling down and hitting the rock protection fence, and all was caught by the camera. Alarms were sent out. The responsible geologist of Salzburg was informed, ÖPB was informed. They were able to send the maintenance crew out. They had the chance to immediately do a visual inspection of the situation on site. And this is how it looks like. You have again the image. You see here the situation with the rocks in the catch fence. You see here what happened. The tilt sensor at the pole next to this rock mass installed at 1 meter above ground showed 75 millimeter of rotational movement. ÖPB went there, fixed it. We sent it back, set it back to 0, and yeah, and this showed how well this system works, and they got what they needed. They know what was going on. They could do a visual inspection. They could do proper planning of their maintenance, and yeah, we are up to install a couple of more of these rock protection solutions for Austrian Railway in the coming weeks. So this was a quick overview, 27 minutes. So it's before Christmas, and it's time for some question and answers. We have, hopefully I will not be surprised, similar to the Santa Claus here about your questions, but I will try to answer them. And if you have additional questions, please feel free to reach out to me, and I'm happy to get in touch with you directly. So I'm done.
Cool, thank you, Peter. Let me just see. Okay, we've got a few questions. First one is, what is the main difference of the InfraGuard system if you compare it with systems which rely on LoRa communication technology?
Okay, I tried to outline that in my slides. You know, as the InfraGuard relies on our flat mesh communication technology, it allows us to be responsive. So basically, the flat mesh network is always listening. The nodes are always listening, also between scheduled readings, and the nodes can communicate to each other if something is happening, and you would have no latency to get an event reported to your web platform. And this is the difference in LoRa. You need to wait until the next reading is taken, and then potentially you can increase reporting and so on, but you might miss out an hour, 30 minutes. So there's an advantage of this network intelligence that comes with the flat mesh technology.
Thank you. Another one, what is the key difference of Sensei rockfall monitoring solution compared to the other rockfall monitoring solutions available?
Well, of course, there are a lot of solutions in the market. I mentioned at the beginning that you can also use other technology to monitor areas like, you know, as at LiDAR. You could use potentially photo monitoring, also combined with our camera, by the way. But the difference is that we have a modular system. Yeah, and I have shown in the slides that we can detect small rocks, medium, larger sized rocks. We have, you know, a modular system, you can only use tilt sensors as shown in this example from land. You can add raw wire sensors if you also want to understand how quick the rock protection fence is filling up this material. And you can add a camera for visual inspection. I think that makes it quite unique compared to other solutions.
Okay, so this is the last question. So if anyone else has any other questions, please feel free to put them in. Okay, so the last question we have so far is, what do you think will be the next developments in rockfall monitoring?
Well, I think, as I mentioned, there are different technologies, and I think what is a quite interesting one is using images or pictures taken, for example, from a sensitive camera, using them photo monitoring technologies from companies like NASCAR from Italy, or you can also use potentially your mobile phone to take images and from the same location at a certain period process these images. So I think it will enable us to use simple tools that are available, and with some intelligence and some processing power and artificial intelligence, we will be able to get a good understanding if something is happening in the rock formation, if small things are moving. And I think we are also looking into using the images that we have from, I don't know, 1,500 cameras that we have in the field to do more or make more out of this image. And I think this is something where we will see some development in the coming months.
Okay, thank you. We've got one more question. Does the data collector on site store data locally in case there is a break in communication to the data center?
Well, in this case, you know, the data will be collected by the gateway because we have the mesh network. So the data might be stored until we have connectivity via cellular connectivity to the server again, but we're not missing data. It's not at the node level, it will be stored at the gateway level. And then as soon as we have connectivity, the data will be sent. I know that, for example, our Geo1 nodes, they also store data on the node because the communication is different, yeah? Because it's a lower communication, it's a point-to-point connection. And if there's a problem, then they store the data at the node level until they can send it to the gateway and then to the server. In our case, the gateway is up and running. It will store the data there, and then it will communicate as soon as we have cellular connectivity at the gateway.
Another one. Oh, just go back. So how do we define the density of the sensors?
So basically, it is always a question of the risk. Yeah, if you have a rock protection fence, you know there's different ways or different design. Yeah, as I said, there's a design load, impact load. The distance between the poles, basically, if you want to install at every pole a sensor, this determines the number of sensors. Yeah, as we have seen at the example at land, I would start with a tilt sensor. Yeah, if I'm worried about smaller medium rock material that will fill up the protection net and it requires maintenance, I would add raw wires. And if it's a really critical situation, I would add a camera. Yeah? So this is a modular system, and basically from tender documents I have reviewed recently, normally the number of poles defines also the number of sensors. Yeah? If the whole area is critical, you could also say, okay, I want to monitor the central part, and you only install sensors in the central part. But basically, normally one sensor per pole is a good starting point. And the distance can vary. We have seen 1,500 kilojoule, maybe 5 meters distance. We can have big protection nets where the distance between the poles is 8, 10, 15 meters. So it depends on the requirements on the site.
Okay, I think that's the end of questions. But yeah, like Peter said, if there are any more questions, you think of any more questions, you can email us at info@sensive.com. So yeah, that brings us to the end of our 2024 webinar series. I just wanted to take this opportunity to thank all of you that have joined us so far. We will be announcing our January webinar in the new year, so please do keep an eye out for that. Thank you so much, Peter, and thank you everyone who joined us. Happy holidays from all of us at Sensive. Wishing you all a joyful holiday season and a wonderful new year ahead. Thank you all. Goodbye.
Bye.